Hi, I'm Sharad, and I'm a Principal Analytical Training Consultant here at SAS. In this video, I'm going to talk about feature selection using Graphical Lasso. Today, high dimensionality data is just a reality, and you deal with enormous features. Redundancy, irrelevancy, curse of dimensionality, sparseness, and overfitting are common problems with too many features. Therefore, methods are needed to find the best inputs to be used into the modeling. This will lead to simpler models, shorter training times, and improved accuracy. Variable clustering is one such method of feature selection. Variable clustering groups similar variables together. By clustering inputs, you do three things. One, you detect redundancies between the variables. Two, you understand the underlying structure between the variables. And three, you reduce the number of variables. SAS Via implements Graphical Lasso for variable clustering. The variable clustering node in Model Studio runs the gvarclust procedure. The node divides a set of variables into disjoint clusters and creates an undirected graph. The graph generally consists of a set of vertices and edges between them. Vertices, or also we can call them as the nodes, are set of objects or entities that are connected, and edges, we can also call them as links, are the connections representing the relationship between the nodes. Edges can have weights that can vary or they may be fixed. You can also see what parts of the graph are isolated or less connected to the other parts of the graph. This method is often used in social network analysis, where you look at who is connected to who. Graphical networks are actually the mathematical structures used to identify pairwise and conditional independence relationship between the entities. Here's a simple example of a correlational network. Now in this case, if two variables are correlated, then the corresponding nodes are connected by an edge, but not otherwise. Therefore, the absence of an edge between two nodes indicates the absence of a correlation between them. So you can set up a matrix and incorporate information about entities in terms of how close different entities are to each other in this context. Here, in our example, the entities are going to be the variables. However, such pairwise correlation could be spuriously induced by shared common causes. Let's take a little deep dive here. For instance, a burning fire causes both smoke and heat. Smoke and heat are always observed together and thus are believed to be indirectly correlated. But this does not mean smoke and heat have any direct influence over each other. In some sense, we are showing here that fire is connected to smoke and it is also connected to heat. But if you see that there is no connection between smoke and heat, we call that as conditional independence. They are both connected through fire, but they are independent. Here in this example, we used a correlation matrix for triviality. Conditional dependency among variables is actually interpreted by estimating the inverse covariance matrix, also called as the precision matrix. Let's take a little deeper dive inside this precision matrix. The off-diagonal elements here correspond to partial correlations, so the zero value imply conditional independence between the pair of variables. The conditional independence provides a better model for understanding the direct link between variables than simple correlation analysis does, which models each pair of variables without considering other variables. A lot depends on the sparsity of this precision matrix. Sparseness refers to a matrix of numbers that includes many zeros or values that will not significantly impact a calculation. A regularization parameter rho is used to control the sparsity of connections among the variables. The higher the rho value, the more regularization and the sparser the inverse covariance matrix would be. Larger rho values requires a stronger correlation between two variables for them to be clustered together. The default value of rho is 0.8 in Model Studio. The higher the rho, the fewer variables are in each cluster and vice versa. I'm now going to show you how the variable clustering process uses this rho. So let's eyeball. In general, the clustering process starts with one variable per cluster, and the number of variables per cluster increases with additional clustering steps. Correspondingly, the total number of clusters decreases with additional clustering steps because clusters in previous steps are merged. The algorithm performs sequential steps of estimating the inverse covariance matrix by using the regularization parameter from large to small, which impose different sparsity constraints on the estimation. The sequential steps eventually produce a set of nested clusters that are originated as a hierarchical tree. So when will this process stop? There are three threshold properties that stop the clustering process when one of the threshold is met or exceeded. 1. The maximum number of clustering steps. 2. The minimum number of clusters. And 3. The maximum number of variables per cluster. Now that you got a fair idea about the variable clustering process, I would like to move into SAS software and do a demo. One final thing before we jump into the computer, this demonstration that I'm going to show you comes from a class that we offer called Advanced Machine Learning in SAS Via. Take a look down below. We will put a link to that class down there as well. I will show you how you can perform variable clustering for feature selection and feature extraction in Model Studio. We will discuss some of the property settings and interpret the results in Model Studio. We will be using the variable clustering node for this task. So alright, let's go ahead and jump into the computer. I have logged into SAS Via and I have moved into Model Studio. I have started up a brand new project here. You can see the name of the project here. I have given the name of the project as gvarglass and loaded the data in memory. We are looking at the data tab on our project, and this data is about a fictitious telecommunications company. The input variables include demographic type variables, variables that describe product usage and type, billing data, and customer service and call center information. The main goal here is to use input variables to predict the churn event, or you can also do discovering patterns using unsupervised learning, or you can do the feature engineering as well. In this video, our focus would be on doing a kind of a feature engineering. You can see there is a warning coming up, and that's a usual warning in Model Studio. We need to specify a target variable even if you want to perform the unsupervised learning. Defining a dummy target variable is mandatory in Model Studio. So what I'm going to do is, first of all, I'm defining a target variable here. In this data set, churn is the target, which is a binary target. So let me find out churn. I have selected churn and I'm changing the role of churn variable from input to target. So we have got the target variable defined here. That warning has gone away. And now we are going to create a pipeline. So let's move to the pipelines tab here. By default, you will be getting a data node here. I'm right clicking and adding add child node, going to the data mining pre-processing group, and I'm going to add an imputation node. Variable clustering node is actually going to ignore all the observations which are even going to have a single missing value, the property what we normally call it as a complete case analysis. So even variable clustering runs on complete case analysis. Variable clustering algorithm is going to consider only those observations which are completely filled. So this is a good idea to get an imputation node here, and the default imputation being done here for the class variables, the count is going to be used as a default imputation method. Count is nothing but the mode value. And for the interval inputs, mean imputation is going to be performed by default. So we are going to sticking to the default input methods only. Just below this imputation node, I'm right-clicking the imputation node and I'm adding a child node again using the data mining pre-processing group, and I'm going to get a variable clustering node added just below this, the imputation node. Now, here if you see the variable clustering node on the right-hand side, it is showing you all the properties or the options of the variable clustering node. One of the important property here is the cluster representation property, and there are two options for you, best variable and cluster component. This is the property which can be used in order to derive variables which can represent the cluster, what we call them as the cluster component. So we are going to talk more about these things later while I'll be showing you the results. But as of now, we are just go with the default, and the cluster representation has been kept at the best variable. I have not done any changes here. The number of representative variables just below that is by default 1. It means one variable is going to be selected to represent each cluster. All right. You also have an option of including the class inputs. It is a good practice to run the variable clustering node only onto the continuous variables, but you do have an option available wherein you can include the class inputs. When you check this option, including the class inputs, behind the scenes, it is going to create the design and the dummy variables, and then those design and dummy variables are going to be used in order to create clusters of the variables. So even I'm not, this property also I'm not changing anything over here. If you scroll down more here, see at the bottom you have a property called as clustering row value. We talked a lot about the row value, which is a hyperparameter here, which is a regularization parameter which you need to set as a user. And the default value of this clustering row value is 0.8. We will not change its value right now. With all these default values of the properties of the variable clustering node and the imputation node, I am going to run the pipeline. So let me click onto the run pipeline button here. All right, here we have got the results. So let me open the results of the variable clustering node. And here when you see the clustered variables network, the very first window, and the clustered variables table, the window just adjacent to that, both of these indicating that only one cluster is created that has only two variables or the two vertices in it. Why? Why this kind of thing is happening? This might be because of a higher value of row that leads to dropping most of the connections between the variables. Larger row values lead to sparser precision matrix and require a stronger correlation between two variables for them to be clustered together. So let's consider tweaking some of the key properties now. I'm closing the results. And we are going to change the optimal cluster selection method. Right now it is none. I'm going to change it to penalized log likelihood. The clustering row value, if you scroll it down, I'm also going to change the clustering row value from 0.8 to 0.5. We are reducing the row value from 0.8 to 0.5. We are still keeping the number of clustering steps to 6. Two properties we have changed. The optimal cluster selection method being changed to penalized log likelihood. Penalized log likelihood calculates the penalized value at each clustering step, and the optimal cluster configuration is determined by the clustering step with the lowest penalized value. And a smaller row value from 0.8 to 0.5 is a less sparse precision matrix and decreases the number of disconnected components. So with this change, let me get the variable clustering node run. Let me open the results. And let me expand the clustered variables table first. Now the first column has cluster membership against each variable, you can see. And if you're scrolling down, this shows that there are 4 clusters created. Cluster 1, cluster 2, cluster 3, and cluster 4. 4 clusters got created here. And each cluster has a different number of inputs. The second to last column here, the variable selected, this has information about the input variable selected, which is yes, or not selected, which is represented here with a no. And this is being done within each cluster by the node. Now the main idea here is to select one or more variables from each cluster as a cluster representative. The variables that contribute the most to the variation in that cluster is chosen as the representative variable. The representative variables are used as input variables in successor nodes. The other input variables are rejected. This is the feature selection idea of variable clustering. You can see the last column. This shows the loadings of the first principal component. I'm going to show you the loadings in a more detailed way in the other output window. Closing this, now I'm going to expand the clustered variables network. This is a visualization. Undirected graph is being created for us. And this is actually a spatial map that gives the orientation and relative distance of clusters and cluster members. Cluster members with a stronger link are connected by a thicker line. There are clearly 4 clusters standing out in different color shades here. Around 30 vertices appeared in this network graph. This means that the remaining variables did not qualify to appear in any of these clusters because of their weak partial correlations and will be passed as inputs to the subsequent node into the pipeline. So the variables which are not appearing in this network diagram, they are automatically going to be set as inputs. They won't be rejected in the subsequent nodes. You might also want to further decrease the value of row so that more variables appear in the network. Let me zoom out this a bit. Now you will be clearly seeing the kind of clusters and the kind of members we are having and the kind of relationships we are getting it over here. Closing this and scrolling down into the results window. And I'm expanding the output window. This is the cluster summary table being shown it has gone up to 6 steps. So recall that the default number of clustering steps was 6, and that's the reason it has gone up to 6 steps. There is no guarantee that it is going up to 6 steps. It could be lesser than that, but it won't go beyond 6 steps. So when you specify the number of clustering steps, that is going to be the maximum value. Now, by specifying number of clustering steps to be more than 1, you performed variable clustering at multiple row values, which decreases at each step. Just to remind you that we had got selected row at 0.5. So the row at 0.5 specified the initial row value for step 1. And then row was 0.5 square in step 2, 0.5 cube in step 3, 0.5 to the power 4 in step 4, and so on. So the lowest penalized value is obtained in step 4 here, and that is the resulting cluster solution. If you scroll it down, you will get to see that. If you scroll it down, and here you can see the lowest penalized minus 2 log likelihood value has been getting, you are getting it in step number 4, and that is what the optimal solution here is. So these sequence of steps yields a hierarchical structure of clustering, which is represented here in the form of a dendrogram. Now, dendrogram is a very common graphical representation of a kind of a hierarchical clustering algorithm. Here you can clearly see that there are 4 clusters in the dendrogram. This is 1, 2, 3, and 4. You can clearly see the usage-related variables are united in one cluster. Most of the variables related to data consumption, this one, the top one, are in another cluster, and the variables related to ethnicity and region are actually clustered together: Hispanic, Caucasian, urban, and so on. The output also has information. If you scroll it further down, the output also has information about the principal component analysis run in each cluster. So within each cluster, a principal component analysis is going to be run, and the first principal component is going to be computed. For example, principal component analysis here ran on 10 variables. There are 10 variables in the first cluster underscore class 1, and the first principal component is being computed here. It also shows how much each variable is actually explaining variation in the first principal component of this cluster. If you scroll it further down, you will see the amount of variance explained by each of these variables in the first principal component. And you can see the calls total. The calls total is explaining the maximum variation in this cluster component. That's why this has been chosen as the representative variable for representing the cluster number 1. So the calls total variable explains the maximum variation, and that was the reason this was selected to represent this cluster. If you scroll it further down, you will get to see the loadings, and these are interpreted as the coefficients of the linear combination of the variables from which the principal component is computed. These are each principal component is actually a linear combination of the variables. And in this case, the variables included are the variables which belongs to that particular cluster. The loadings are actually the coefficients or the linear coefficients which are going to use to construct the cluster component. Now, variable clustering can also be used for feature extraction. Each cluster can be described as a linear combination of the variables in the cluster. The cluster component is derived by taking the first principal component when running a principal component analysis on the variables in that cluster. And in this context, it is called the cluster component, and that can also be used to represent the specific cluster. So now that you have cluster representation property in which you can choose to export the first principal component for each cluster, with the cluster component option, the first principal component is extracted from all the variables in a cluster and then output as a new variable, which we call it as underscore class 1, underscore class 2, underscore class 3, and so on. And the original cluster variables are then rejected. The total number of generated component variables actually correspond to the number of identified clusters. If your solution is having 4 clusters, it means 4 cluster components are going to be extracted from each cluster, and then those can be used as the extracted features and those 4 cluster components as the input variables in order to represent all the other variables. So we have almost reached to the end of this topic today. Let's summarize. Variable clustering finds groups of inputs that are partially correlated as possible among themselves and as conditionally independent as possible with other clusters. From each group, representative inputs can be selected based on how well they represent the group or by creating the cluster component from each group. Graphical network analysis is visually interpretable. Thus, it is very helpful in terms of understanding the relationship between variables by looking at the graph. If you want more information on this topic, take a look at the links below. Please feel free to leave me a comment and ask me a question. If you are interested in more tutorials and if you like this one, subscribe to our channel. Thanks a lot for watching. See you later. Bye-bye.